So, good morning to all of you, and good morning in particular. I see a few students in the room. Are they students from the university here? Can you raise your arm? They're all in the back, so great. So, I'll speak loud. So, what I would like to do today is really to give you some kind of an overview of maybe what we should think about climate change. I'll talk a bit about what happens in the region here, but I'll try to put it more in a kind of a conceptual way or philosophical way. I'm giving a similar talk tonight in French, and so for me this will be a bit of a rehearsal. It is largely tutorial, so I'm not going to come up with a lot of recent results. But so what I would like to do is really to talk about what I think have been and are still grand challenges for the scientific community, going backwards in time and looking at how our views have evolved. In fact, probably at the beginning of the 20th century, one of the great challenges that was probably put on the agenda of the funding agencies, if they had existed, was to predict weather. Weather was difficult to predict, but it was very societally important to know what will happen in the next days because the economy was so much affected by it. But then more and more people started to think about long term and to want to predict or maybe project how climate would change. And then in the last 20 years, the realization that the Earth is in fact a complex system with a lot of interacting processes and also feedbacks that create a certain stability in the Earth, and the danger that its stability be modified, perturbed by human activity became really an important issue. And so now we are moving slowly towards another philosophy. We realize that climate needs to be maintained in a certain bounds, and the bounds was chosen to be something like 2 degrees Celsius warming. We have to see how we're going to manage the Earth system, what measures we're going to take to stay within those 2 degrees. So I'd like to go through those 4 challenges and see exactly what we have learned from them. The first one is the prediction of weather, and what I would add, doing some kind of numerical weather prediction. Things started to be really dominated by the philosophy of Newton. Newton that, or maybe also Laplace, who said, well, once you know the state of a system and you know the law of physics, you should be able to project its evolution in the future. And so people started to take that idea, and in particular, Bjerknes and in the UK, Bjerknes in Norway and Richardson in the UK, to start to basically solve the first principal equations applied to hydrodynamic medium, and to solve the equations and do a prediction. And in fact, I said it was a very deterministic view. Simon-Pierre de Laplace explained that once the state of a system is known, and the law are known, well, you can really probably calculate the evolution of the system forever in front of you. So Bjerknes started, Richardson tried to solve the equations, and to do that, he started to put a chessboard on the Earth, in particular over the European regions. He had a number of observations to initialize his model. He started to discretize these equations, introducing numerical approaches, and he tried to do a forecast for the next day. He was an ambulance driver during World War I, and that's during the period where it didn't work that he did this calculation. It took him several months to do by hand the evolution of one time step or a few time steps to get a day ahead of him, and then he realized that his prediction was in fact not very good. In fact, he failed in doing this prediction. We know why today. And in fact, he also realized that it would take a lot of time to do that, and if they wanted to do that every day for having a real prediction, he couldn't do it on himself, but he needed to probably create a theater like the one you see here and put a number of people, would each of them do the same operation on a sheet of paper, then pass the sheet of paper to their neighbor. He kind of invented the concept of parallel computing. So we had to wait until after World War II. So the Richardson was then operating in 1914 to 1918, so during World War I. But then the first electronic computers became available. The ENIAC computer was made available, and the scientists at the time, I'll show you in a minute, tried, Julie Charney and John von Neumann in particular, a meteorologist and a mathematician, tried to work together, and they solved a certain simplified form of the equation, the quasi-geostrophic approximation, in order to basically eliminate a number of waves that had very little physical meaning in their computation of the weather, was distorting completely the numerical prediction of that was the case from the previous Richardson calculation here. And so finally they were able to do a first forecast. So this is a picture of the first computer, the ENIAC, around 1950, and you see Charney and von Neumann here working together. I mean, you see here more on the computer. And of course, today things have changed very much. We have a real growth in computer power so that we can do a number of things. Now, this was a very deterministic view, but of course, already around 1900, Poincaré in France was studying basically celestial dynamics, trying to solve the three-body problem, and then found out that there was a chaotic component to this, and so predictability was therefore limited. Lawrence at MIT then made more calculation about this and showed that, in fact, indeed, the atmosphere is very chaotic and you cannot predict things more than a few days or maybe a few weeks in front of you. And so the deterministic complex was replaced more and more by, recognizing the chaotic system, and ensemble predictions were made in order to address the chaotic nature. And so the kind of things that is done then today is really this probabilistic forecast, in which you recognize, first of all, that your initial conditions that were so important to calculate the future evolution of the system are subject to a certain uncertainty. And because, as Lawrence has shown, for example, the solution depends so much on the chosen initial condition, you have this uncertainty in your prediction. And so you start, as seen here, by having kind of slightly different initial condition, maybe slightly different conditions in your model on certain parameters, so that you get into different type of forecast based on the choices you made. And finally, you get a probability here, for example, for precipitation. This is now done today. And if you look today at the accomplishment that we have made over the century, this is here a forecast by ECMWF of the weather some time ago, and then the a posteriori verification by looking at satellite observation. You can see how similar the prediction and the real observation are. It has been an enormous improvement in the weather forecast, and you see here, for example, the anomaly correlation, in this case of the geopotential at 500 hectopascal. You see as a function of time how better we are. The correlation now becomes almost close to 100% if you think about 3 days forecast. We still have to do better, of course, when we look at longer time prediction, like 10 days, but this has been really what some people call the quiet revolution in numerical weather forecast that has happened over the last century. So that brings us to the second grand challenge, and this is to try to predict, maybe I should say project, climate change. I say project because we know that we cannot predict the state of the atmosphere. more than a few weeks ahead of us, but we can do some projection. We can use the techniques that we have learned in the weather world to apply that to the climate system. And of course, it all started with Fourier, also in France, who kind of discovered the concept of the greenhouse effect. He called it a glass ball at that time. Didn't quite understand what was happening, but the concept was there. And then Arrhenius was the first probably to do some kind of back of an envelope calculation to show that if all this carbon coming from coal in the mine was released into the atmosphere, we would heat the atmosphere by a few degrees, perhaps 5 degrees. And he was very happy about that because he felt that that could compensate for the next glaciation that he had probably that he was fearing, especially being in Sweden, where, of course, glaciation means something. And so, basically, the starting of the calculation of how greenhouse gases would affect the system was put on the agenda. Some simple approach were taken. But today, of course, we try to put that in a very broad framework of climate models. And a climate models is not just the atmosphere, as we saw in the weather, but it also includes an ocean, which has its own dynamics and its own, basically, equations to be solved. The two have to be coupled because of the exchange of energy between the two. And, of course, you have to start putting more processes. The vegetation on continent, the change on land surface are important. The sea ice issue, the cryosphere in general, and then people add things like atmospheric chemistry or ocean biogeochemistry in the system. And this is a very complicated system. It's also a very nonlinear system that is then addressed by basically using the same approaches that we have been using in meteorology. And you see here, for example, a picture of the increase in the complexity of climate models. We started here in the 60s, where we really had an atmosphere with some land attached to it, coupled to an ocean model. But now you can see that today we have much more component, and you see also this can be graphically represented. And the more complex you go, the more problem you encounter. And basically, it's not a kind of science that a small group can perform. You need to have large teams of people, international team very often. So one of the issues, of course, is to look at the radiative forcing. And you know that CO2 is kind of trapping radiation in the system. And so this radiative forcing is changing, of course, as a result of releasing anthropogenic CO2 in the atmosphere. And so a very important aspect now to those climate models or Earth system models is to add a carbon cycle calculation so that you link essentially the behavior of carbon in the Earth system with the meteorology, with the climate itself. And you can see here, for example, the radiative forcing that comes from the release of CO2, compensated by some sinks from atmospheric CO2, both in the ocean and in the biosphere. And in particular, the component associated with the biosphere can be extremely fluctuating, depending if you have droughts or how the climate of the year is behaving. But today we can monitor all that, and ECMWF through, well, in fact, the Copernicus project, and particular CAMS, Vincent Ripoche is here, is leading this project, provides now every month inversions of the CO2 flux. This is for 2012, September, and you can see upward fluxes, so from the surface to the atmosphere, or downward fluxes from the atmosphere to the land and to the ocean, and this is evolving a lot, but it needs to be very well understood if we want to understand the fluctuation and the evolution in the Earth system. Now, this was supposed to be a movie, but it's not working, but just wanted to show you here how, for example, the model now have improved, not only in terms of complexity, but also in terms of resolution. This is a climate model run with a 14-kilometer resolution, which is perhaps a bit at the edge of what's done today, but showing you essentially the complexity of the transport, in this case, of water vapor. So climate has changed, and of course, we have been looking at that, the community has been looking at that, and you all seen this curve that shows you the mean temperature, or at least the global evolution of the deviation from a constant, from a mean value, showing you these trends. What is important, this is why I'm showing you this curve in particular, is that around 2000, the temperature started to be relatively constant as a function of time during about 10 years. And so a number of people were kind of saying, well, it seems that climate is not warming after all. And so we heard a lot of reaction in the political circles to say, well, it seems that the greenhouse effect is not functioning and that it's all kind of fake, what we have heard up to now. Well, the first thing to notice is that since about 2014, the temperature increases again, and in fact has increased pretty dramatically. You see that in the last year, the increase has been compensating in a way for the slowdown of the increase. And that's just to highlight that on top of a trend associated with more CO2 in the atmosphere and other greenhouse gases, in fact, we have a lot of fluctuation in the Earth system, and so it's very difficult to disentangle trends from variability, and I think politicians need to learn that the system is complex, that the system is affected by a lot of internal variability, and that we were not going to have a very linear, easy response of the temperature to CO2. We will also have to learn that the warming is not uniform, that you have regions that are more susceptible of temperature change, like in particular the polar regions. And then if we look at precipitation, we will see that the response to what we have seen is a complex response. There are regions with more precipitations, there are regions with less precipitation. Very often we say that where it's humid, it's more humid. When it's dry, it's drier in the future, but even that is not completely true. So let's now move a bit to the region here, to Réunion Island. And of course, you see here on the maps where Réunion Island is in the southwestern Indian Ocean, just east of Africa, which is a region, as you see, characterized by high pressure, so an anticyclonic region. And I took the situation today on the weather. You see the surface pressure with the high pressure a bit south of Madagascar, and you see the surface winds, Alizé winds from the east. You see the precipitation forecasted for today, so it doesn't seem too bad, so we're pretty happy. And then you see the sea temperature. This was a few days ago, where the temperature of the water is warm enough to have a few sharks around, so don't try to go and swim. But looking at the evolution, this is a map established by Météo France. The annual evolution of the temperature shows clearly a warming in the region. If we look at precipitation, again, it's more complicated. You see here essentially the numbers of days where the precipitation was reaching more than a certain number of millimeters, so the green is a pretty strong rain, and you see that it's very difficult to get a trend out of that, but you see a large fluctuation from year to year. There have been a number of papers recently published about what people say the curious case of Indian Ocean warming. It's mostly in the northern part. You see the upper curve showing you essentially the warming of the Indian Ocean. And what you see is that in the western part, the warming seems to have been larger. And this might be related to the monsoon circulation, rainfall in the northern part in particular. But so you see that basically the Indian Ocean warm pool temperature has increased by about 0.7 degrees between 1901 and 2012. And now we see that during this period, the Western Indian Ocean is increased by temperature has increased by about 1.2 Celsius. And in fact, I don't know if I have a graph here, there seem to be some correlation with El Nino in the temperature, but I leave it to specialists of that question to be more detailed about it. Now, the region, of course, is affected by hurricanes and typhoons and large weather events. You see here a picture of what was the largest cyclone. On the left, you see the trajectory of many cyclones in the past, and you see that Réunion Island is there in the middle. What is interesting is to see that as a function of time, the area, the line where the hurricane have had a maximum intensity, and here we go from 1980 to 2015, seems to have been moving, in fact, towards the pole, including getting a bit closer to La Réunion, and so it may be part of change in the general circulation of the atmosphere. You see the kind of study made here for different parts of the world, and it seems that in all cases there is a trend in the location of the hurricane that is poleward, showing you probably a broadening of the tropical regions associated with climate change. That's a good possibility. Sea level, of course, is important. It's recorded all the time by satellite like JSON, Stopec, Poseidon here. And you see that the changes over, let's say, the last 22 years that has been recorded shows that there have been some increase in the surface height, in particular in the region here where we are today, perhaps something like a few centimeters. You see the same thing here. So what about the future, and what can we expect? So to do that, of course, we need to rely on scenarios. Since we cannot really do a prediction, we have to do really projection based on possible emission scenario. And so you know that IPCC in particular has been using 4 major scenarios. First of all, the largest one called RCP 8.5 brings basically a warming of 8.5 watt per square meter. That is, to a certain extent, business as usual. So if we do nothing, we might be very close to that curve. Then you have more moderate ones, and the less perturbed case, RCP 2.6, has been chosen so that we have a case by which we keep the temperature change to about these 2 degrees that I was talking about. So this is now the response to those scenarios, global average, calculation made between 1850 and 2300. The yellow curve shows you the past situation, which reproduce very well what is observed, and the models need to do that to gain confidence in how they will project the future. And then you see, for example, in red, the situation for RCP 8.5. If we are in 2300, we get about 8 degrees on the average warming. But if you take the lowest scenario with RCP 2.6, then you can see we do not go much about 2 degrees increase above pre-industrial. So this is, of course, a global picture. And of course, it's not a uniform response of the Earth system. And what you see here is the year where essentially the global mean temperature gets outside the bounds of the natural variability. And so you can see more or less when the cities that are listed here will perceive that there is a real climate change occurring. And it's ahead of us, but it's not that far away. And so this is one way you can pick up or at least represent the kind of things we are expecting for the future. So other aspects, of course, of the climate system are projected. One is the global sea level rise. You see here that, again, it depends on the scenario. But we're talking in 2100 of a change that goes from about 40 centimeters to almost 1 meter, and so it becomes relatively significant. Now, what is interesting also to mention, and that was in the last IPCC, is that what happened, the scenario, in fact, is not the key issue. What is the key issue is the total cumulative CO2 that you have in the atmosphere. The scenario, in fact, tells you perhaps that it will happen sooner or later, but you can see that there is almost a strained relationship between the temperature anomaly that you calculate and the amount of CO2 that you are putting in the atmosphere. So we know very well now that we put so much CO2 in the atmosphere, we can expect a temperature anomaly on the global scale. Now, these mean values are perhaps a bit misleading for the understanding of what will happen. It's probably more important to look at some of the extreme and rare weather events, so strong weather events, as we observe them sometime, because in reality it's not just one value, but we have a distribution of occurrence of a number of events, like temperature change, for example. And so the average that I showed you, yes, will go up, but more important is the tail of this distribution, where we will have more hot weather. And that's here shown for the temperature, but you could show similar curve, for example, for the precipitation that is probably more felt even than the temperature change. So some people start now to look at statistical information about the likelihood that extreme events will occur. And I saw an analysis from the reinsurance. They looked at 100 extreme weather events in 2011, and they derived that about 65% of them were attributed, at least in part, to climate change by looking at the distribution, how the distribution has changed with the past. And so slowly we start to realize that when we have a big event that is occurring, that probably climate change is partly responsible for that. So let's look at an evolution in the region. You see here the black circle shows you where Réunion Island is, and I'm going to do it again. This is a movie from it's a Max Planck model that shows the gradual warming here that occurs and that will affect between, this is RCP 8.5, so it's the most intense scenario. You see that we expect some warming, and if we look at precipitation, the more, you can see the changes here occurring. So let's do it again. So the red is more intense precipitation here. Let me see if I can get it. So you can see that it's not very clear that precipitation will change dramatically, at least based on this model, change in Réunion Island. So Météo France did also a number of studies. You see on the left-hand side the anomalies in temperature. This is now for year 2080. It's also RCP, well, 6 on the left, 8.5 on the right. You see the warming occurring in the region. If you look now at the precipitation, you get, again, 6.0, RCP 8.5. Let's take the most advanced or the most important RCP 8.5. And you see that, again, it's not completely clear, but they seem to be here that in the wintertime, in particular, you see less precipitation and not very much changes in the summertime, according to the model of Météo France that is shown here. So I'm going to pass this. Okay, now let me go to the third grand challenge, which is really understanding the Earth as a complex system. And so there are a number of issues that were put together. One, of course, I mentioned Lawrence, who showed that basically the Earth is a non-predictable system. But we also see, for example, the analysis of the ice core that shows basically that temperature, concentration of greenhouse gases were really working together. So there's been a lot of issue, the Gaia hypothesis from Lovelock, that kind of brought the idea that we have to look at a complex system. So this is, for example, the Antarctic ice core in the last 800,000 years, showing you, of course, the temperature in the middle, and then CO2 and methane. And you can see that, of course, they have been fluctuating together, which shows you very much the connection between these different quantities. But it also shows you that today we are getting really out of the range of the natural boundaries, and we don't know. We have no precedent, at least in the last million years or so, of something that strong in the system, and so it's not clear how the system will respond. And so, yes, if the Earth is resilient and is in an equilibrium state, well, we might change a bit, nothing really will happen. But if we get into a less resilient Earth, we might come from a situation like this to a situation where we jump into another equilibrium. And so the question really is, are there tipping elements in the Earth system that are such that we could flip from one state to another? And this is a map of places where there is potential for flips from one stable to another element. And they might be located in different parts of the world. For example, permafrost goes away, methane might be released because there's a lot of methane underneath, so we might have outbursts of methane that will kind of be a positive feedback in the system. The Amazon could collapse. There are a number of those issues. There is certainly instability of the greenhouse ice sheet, a bit far away from here, but at the end, all that will come together and have an impact. And so the concept today of planetary boundaries is introduced as something that could be used for policy making. You have a number of different quantities. I mean, climate change, but you can talk about ocean acidification, you can talk about land system change, aerosol loading, whatever. And so the center of the graph is perhaps where you can live in a relatively safe environment. But what happens if you break those boundaries and you go beyond them? And so in some cases, you might be beyond some of the limit of the boundaries that are there, and that's a way by which you can apply things. But you have to have a systemic approach to this type of discussion. So it leads us to the fourth grand challenge, which is really to manage the Earth system. And so today, of course, most people are convinced that climate is a challenge for all of us in the next decade, perhaps the greatest challenge that humanity has faced for a long time. And so even private corporation, public administration are really exploring ways to reduce environmental risk, but also to find opportunities, economic opportunities in particular. And so we think that advances made by the science in the last decade remain to a large extent too little utilized. And so this is why you see now a number of climate services who are being established. The problem is that we have to go beyond the physical science that we have been discussing up to now. The science is the basis, but issues related to the economy, to living together, well-being, governance of the community are very important. And this graph, I think, highlights the diversity that you see in order to, at the end, build a real mitigation approach, or maybe, if we don't succeed completely with mitigation, go into some adaptation issue. And so the projection of future climate change resulting from greenhouse gas emission has provided the scientific basis for policy decision. I mean, clearly, there wouldn't be any COP21, no Paris Agreement, if the scientific community hadn't alerted basically the policymakers and had made a number of clear calculations. So now, of course, COP21 calls for measures to maintain the mean warming below 2 degrees and therefore reduce the greenhouse gases accordingly. And so mitigation becomes very important, but of course, there are people who don't believe that it's completely achievable, and so we need also to be ready to adapt to undesired climate change, and perhaps, but that's a debate, to start thinking about climate engineering. So mitigation and adaptation become a central theme, and you can see here a number of issues related to mitigation and adaptation. In terms of mitigation, you know it has to do with renewable energy, with energy conservation, with transportation system, with basically changing somewhat our agricultural system. But now if we look on the adaptation aspect, we start thinking about how to upgrade our infrastructure, building residential programs that are responding, health program, emergency and business continuity planning, and help, especially for the most vulnerable people. In fact, we know that the most vulnerable people to climate are the people who are probably the less rich on our planet. And so mitigation is really the action to reduce the emission. Adaptation is the action to minimize or prevent the impacts, or the negative impacts of climate change. So let's say a word about mitigation quickly. And here's a calculation that I'd like to share with you. You see here essentially two models that shows how basically climate will change in response to CO2 emission. And you see the black line on the graph below that shows basically the 2-degree limit that we do not want to pass over. And so you see that some of the curves remain under the 2 degrees, and these are the curves where the reduction in the emission are at least of 80%. So how will society respond to the need to reduce emission by 80%? Now, here is a model by which you can decarbonize society and limit climate change to 2 degrees. This curve was established in 2010 and showed that if the emissions follow, let's say, the green curve, you start to have a peak in 2011, and then you go relatively slowly, you will achieve it. But the more you wait, and if you start really taking measure, as it seems to be the case, let's say in 2020, you will need a much more abrupt reduction in CO2 emission, and this becomes much more challenging for society. What, of course, this curve doesn't tell you is who is doing kind of the reduction. And, of course, you know that the situation is very different in different countries, but I have no time to talk about that. Adaptation is a complex issue because we have to look really at how society works. We have to look, of course, at the predicted or the projected climate change, but then we have to look at the exposure to people, the sensitivity to a number of processes in society, and finally define the vulnerability. But the vulnerability also depends on the technological, socioeconomic, institutional, and educational capacity. And so all these issues are related, and really society needs to think how to address this. So there is certainly an approach that has to be taken from two sides. First of all, let's say from the physical point of view. We know we can expect, or we can project perhaps what the world development will be, and so what the greenhouse gas emission will be. And so we can look at climate change and finally at the physical of the vulnerability, the physical vulnerability. But on the other hand, the social science community needs to look at things like education, technology, infrastructure, institution, equity, and looking at the end on the adaptive capacity of a society to learn about the social vulnerability of society. And finally, both have to be put together. Finally, if we don't succeed very well in mitigation, we might have to think about climate engineering. And that raises, of course, a number of not only economic issues, but also ethical issues. So there are different approaches that have been proposed. Some are just to manage the way solar radiation basically touches the surface and leads to the heating of the climate system. You can put aerosols in the atmosphere. That was the initial proposal made by Paul Crutzen. You can put reflector in space. You can do a number of things of that nature, change the cloudiness, put aerosols, etc. Or you can start touching the CO2 aspect, basically. And so you can try to modify somewhat the land by planting trees. You can also try to capture and store carbon. But all these approaches have issues because you don't know necessarily what are the secondary effects of all these measures that you are taking. And so the Royal Society in the UK has looked at both the effectiveness and the affordability of these different approaches, and this is being discussed. Models are being run to see the consequence of all this, but of course, more importantly, I think, is the ethical issue. In fact, doing climate engineering is not very expensive. It probably costs a few $100 billion for governments, but you know, there are always governments that are ready to do that because the benefits might be higher than the cost. But there is no international agreement that controls that. So if one country wants to start doing geoengineering or climate engineering, nobody can really legally stop them from doing it. If China wants to start it, the US wants to start. If large companies who are thinking about all these new economic endeavors want to start doing that, and the president let them do that, it could go. And the consequences, especially on regional climate, are not very clearly understood. Finally, let me say a word about communication on these issues. In fact, the scientific community has been always trying to convince policymakers and the public using, let's say, arguments that are rational. We're trying to show things. We're doing models. We show curves. And we still see people that are very skeptical, that have difficulty accepting a number of relatively pessimistic forecasts that we are doing. And I think a big topic of research is about how to communicate scientific information to a public that's not necessarily ready to accept that. So we want to change behavior at the end. But behavior doesn't essentially result, as we think very often, from kind of, providing information, science, education, media. There are other aspects that enter in the game. One are the beliefs. People believe in certain things. That's related to the religious system, the family system, or the personality structure. On the other hand, you have social norms, social construct, political system, economic system that exist. And all that coming together with the information that we provide the values that people then have and that will drive their behavior. And so this is a very complex system that we have to deal with. And so the scientists that most of us here are forced to face communication into a value conflicting contest. And you see here a graph that goes basically from the scientists to the producers, the analyzers, the translator of information, the provider information, the communicators, and finally the users, the public, the people who need that. And in reality, yes, we can generate data, and maybe the strength of our community is adequate. But the integration, the analysis, the interpretation might already be more problematic. The delivery, the translation, including the non-climate context in which we have to put our information, it's emergent and the size of that community is weak. And finally, the adoption, the community that looks at adoption might be relatively large. And you see here the communities, the scientific communities in red. You see the users community, the line in blue. And there are a lot of choices that have to be made along this chain. And that creates, of course, a relatively difficult issue to deal with and to manage so that there is a smooth transition between what we think is important to know and the behavior of people. Conclusions. Well, climate research has certainly made tremendous progress in the last decade. And so today's society is pushing climate of the planet and other critical physical process towards dangerous threshold. The decision maker needs therefore information on how the Earth's social, ecological, and physical systems are linked, how they respond to multiple stressors, and what sustainable solution can be applied. Knowledge must be properly developed, managed, and communicated to avoid ecological and economic disruption and work towards a sustainable future. Thank you.